Hi there, folks. Today we're looking at permutations and combinations. And permutations and combinations are basically used to figure out the number of outcomes. So just like we've been doing when we talk about things like our fundamental counting principle, but permutations and combinations are used in more complicated situations. So if you think about everything we've done so far, we've been choosing one thing at a time. All right. So, for example, we've had like a bag of marbles or something like that, and I've been taking one marble out, then the next marble out, then the next marble out. When we pull things out one at a time, that's when we can use things like our fundamental counting principle. Or we're saying, hey, there's 12 options of this, and we pick one, and there's 12 options here, and I pick one, and there's 5 options here, and I pick one. We're taking one thing at a time. That's when we use kind of those simple approaches like the fundamental counting principle or the probabilities that we've been doing. All right. The second I change this to more than one thing at a time, so again, using that example of the bag of marbles, if I reach in there and pull out a fistful of marbles all at once and have 5 marbles in my hand all at once, now I have to move to something more complex like a permutation or a combination. All right. And so the idea that when I'm taking things one at a time, I use the simple approaches that we've been doing. But when I'm taking more than one thing at a time, that's when I move to these more complicated systems like permutations and combinations. All right. So we use a permutation when the order of the outcomes matters. Okay, so when order matters, so it's the number of possibilities when order matters. And when we say that, it means mathematically, do I get a different result when I change the order in which I've taken these things out? For example, again, back to the bag of marbles. If I want the number of ways that I could get a red and a blue marble, would it matter if the red marble came out and then the blue marble, or if I pulled the blue marble and then the red marble? No, that's the same result. The result is I have one of each, okay, regardless of the order in which they came out. All right. And so that's a situation when order does not matter. But if I'm like lining things up, if it says how many ways can I arrange these things on a desk, all right, now we're talking about order mattering because every time I move something, it's a different arrangement because I'm changing the order. So we have to look for some of these keywords. So does the order, just changing the order, give me a different result? That's when order matters. That's when I would use a permutation. Okay. The way we read this, if we look at this guy, you notice we have this little n and this little r. Those will be numbers. But basically, n is the total number of things that we have, and r is how many of those things we're choosing. In other words, how many things, like how many marbles we're grabbing out, all right, that kind of thing, all right? And so the way we read this is some folks will read this as n objects taken r at a time, so the permutation of n objects taken r at a time. I typically will say it this way. I'll say the permutation of n choose r, all right? So the permutation of n, how many I have, and r, how many I'm picking. All right, and the formula here is n factorial over n minus r factorial. We can also do permutations and combinations on the calculator, which I'll show you that as well. All right, so if I looked at something like this one, it's the permutation of 5 choose 2. So basically 5 is the total number, so that's 5 factorial, over, that's 5 minus 2 factorial. So basically, like, this is like I have 5 different things, and I'm picking 2 of them to put in order. All right. And so if I simplify this, and just thinking about how factorials work, remember the 5 factorial and the 3 factorial, everything from 3 on down is going to cancel out, so I'm just left with 5 times 4, which is a 20. All right? And now I'm going to show you how to do it on the calculator. I have my 2 big calculators here. Let's see, I've got the TI calculator, and I've got the Casio calculator. I'll start with the TI. Over here on the TI, you're going to hit the math button. It's right there under alpha, so you hit math. You go over here to this PRB, and you hit enter, but I messed it up because my big fat fingers can't hit anything. So we go over to PRB. Oh, sorry. And then under PRB, we see number 2 says NPR. And here's the thing, when you punch that in, notice all of a sudden it's stuck an ANS there, it's stuck an answer thing there. It's because it's expecting to have a value punched in first. So when you punch this in, if I want 5 choose 2, I have to punch in the 5 before I go to that math menu. And that's probably the most frustrating common mistake that students make is they forget to punch in that first value. See, now you see it says 5 permutation, and now I type in the 2. All right? And on the smaller versions of the TI type of calculators, like the little scientific guys, the TI 30s, you should see an actual button that says PRB, that stands for probability, and it will bring you to that same menu where you'll see the NPR, you'll see NCR. You have to do it the same way. Type in the 5, then navigate to the NPR button, and then the 2, and then you hit enter, and notice it still gives me the 20, all right? On the Casio, what we're going to do here is we're going to hit this button that says OPTN. That's options, all right? So I'm going to click that options button. And none of these are the options I want. Notice F1 corresponds with list. F2 is, matrix. F3 is complex. We're going to go over to this arrow, so F6. And notice now F3 has PROB above it. That's probability. And I hit that PROB button, and I enter it the same way. I can see the values that I want here, so I hit the 5, and then I hit F2 for the NPR, and then I hit the 2. And again, that's saying the permutation of 5, choose 2, and I hit enter. Now, the nice thing, hopefully you see about the Casio, is notice that menu is still up until I exit out of it. So if I'm doing a bunch of these, I'm going to leave that menu up for the next one, all right? So if I look at the next example here is 12, choose 3. Well, on the Casio, I've already got it pulled up. I hit 12, F2 for the permutation button, and then the 3, and I hit enter, and it gives me 1,320. On the TI over here, I have to type in the 12, and then I have to go to math, over to probability, then down to number 2, then the 3. So I have to keep going back into that probability menu each time. Not a big deal, but there it is. So 1320. And so I want you to see where the formula comes from, but for the most part, you're going to be able to just punch these into the calculator, all right? From here on out, I'll just use my Casio calculator because it's easier and a little bit faster. You use the one that you have. But again, on the smaller calculators, on those scientific calculators, you should have a probability menu or a probability button somewhere, and it should bring you to that same menu. And you also see the factorial button there as well. For example, if we look at this guy, there are 10 finalists in a math competition. How many ways can gold, silver, and bronze medals be awarded? And so the question becomes, does order matter? All right. If I change the order, does it change the result? And the answer is yes, because if somebody was in first place and now I switch the order and have them in second place, it's a different result. They're getting a different medal. All right. So when we're talking about competition, the order in which you place matters. All right. First place, I'm sad to say, is better than second place. All right. It's just the way it is. Okay. So because order matters, I'm going to use a permutation. And I just have to think, all right, how many total objects or how many total things do I have here? And the answer is 10. And how many total am I going to choose, or how many are being picked? And the answer is 3. All right. There are 10 total finalists, and we care about the top 3 in terms of the order. All right. After that, we're not awarding medals. So it's the permutation of 10, choose 3. And again, I can do this on my calculator, 10, permutation 3. Again, make sure you just punch it in the appropriate order. It gives me the 720. And really the most difficult part about some of these things is just figuring out whether it's a permutation or a combination, figuring out if order matters. How about this one? It says, how many ways can a class of 12 students be arranged in 12 seats? And then how many ways can the same students be arranged in 15 seats? So it asks me for 2 different things here. And here's the thing. The word arranged literally means to put things in order. If I say arrange these things, I'm saying put these in a specific order. So then the question, does order matter? The answer is a resounding yes, because it says right there arrange. That means order matters. All right. So 12 students in 12 seats. So I have 12 total seats, and I'm filling all 12 of them with students. So it's the permutation of 12, choose 12. And it gives me 479 001600, if I remembered that correctly. Let me pull it back up. Yep. And that's a lot of seating rooms. So think about that. If I have 12 desks in my room and 12 students, there are, let me put my commas in here, 1,600 different seating charts that I could make, all right? And then if I make a slight change here, let's say I have 15 desks. So now I have 15 total desks, and I'm going to fill 12 of them with students. So I'm going to have empty seats here. Let's see how that changes the number of outcomes. Ready? 15, and then choose the 12. Look at that. It spits this thing out in scientific notation, all right, because the number of arrangements is so big. And so I want you to keep that in mind in terms of how we think about these things. I'm just going to round this off, and that was times 10 to the 11th power, all right? And granted, if I was actually making a seating chart, there's certain seats that I wouldn't leave empty, like the front row, because everybody loves those seats, okay? But we drastically change the number of possibilities when we start changing some of these numbers, okay? How about this one? It says an old spinster has 12 cats. She lines up 4 of them for a creepy cat parade. All right, maybe she puts each of them in a nice little sweater or something like that. Great way to pass the time. How many creepy cat parades are possible? And so again, here, the implication as we read this thing, she's lining them up for a parade, all right? And anytime we're lining things up, we're talking about placing them in a specific order. Being first in line is not the same as being last in line, all right? And so the implication based on the words is that order matters. So it's the permutation. There are 12 total cats, and we are picking 4 of them for the parade. So now I punch it in. It's the 12 permutation 4. And it's 11,880. That's a lot of different arrangements, and you're only talking about arranging 4 things because we have so many options to pull from, okay? So next we're going to talk about a permutation with repetition. And this is basically when some of the things are identical, all right? In other words, there are some things that are exactly the same. So when I switch them, it doesn't actually change my result. Even though order matters, all right, switching certain pieces doesn't change what I have, all right? And so it's the permutation of n choose r. And notice we have n factorial over p factorial, q factorial, dot, dot, dot. Because P and Q just represent the repeated values and how many I have. And there might be one value that's repeated, so I'll only have one number down there. There might be 2 values that are repeated, so I might have 2 numbers down there. There might be 3 numbers that are repeated, or 3 things that are repeated, so I might have 3 numbers down there, okay? So really, there can be as many things as I need in that denominator, all right? For example, if I look at something like this guy, and there is no permutation with repetition button on the calculator. We just kind of have to do this one by hand, all right? It says, how many ways can the letters in the word Mississippi be arranged? And can you see that some of these are identical? In other words, like if I switched this S and this S, would I get a different result? Would it stay anything other than Mississippi? And the answer is no. If I switch the 2 S's, I still have the same thing. So did changing the order change the result? And the answer is no, it didn't. But I'm still talking about arranging, and if I change the order of certain things, like if I change the M and the I, do I have something other than Mississippi? The answer is yes, all right? This is a permutation with repetition. Order matters, but changing certain objects, changing certain values doesn't change the result, all right? So here's how I do this. I start with the total number, so I have to count up the letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 values, 11 letters here. So 11 factorial over, and then I just look and say what's repeated. And hopefully you see, okay, there's I is repeated, and there's 4 I's, so I put a 4 factorial down here, and that basically just represents the 4 I's that I have, okay? And then I say, okay, what else is repeated? Oh, S, there's 4 S's. So that 4 represents the S's, and then there's also 2 P's, so I put a 2 factorial down here. So I just represent the repeated values. And that's it. Now from here, I just have to simplify this thing. Obviously, the 11 factorial and one of the 4 factorials I could cancel out. You know what I mean? So everything from 4 on down cancels out, but I still have another 4 factorial down here. Whoops, if I could write. And I still have the 2 factorial. See, so I canceled one of the 4 factorials. And then from here, I could do things like, 4 times 2 is an 8, and I could cancel with that 8. And 3 times 2 is a 6, so I could cancel with that 6. And now it's just a little bit less work for what I have to punch into my calculator. Again, you don't have to do all that. If you're going to punch this in all in one shot, make sure you put parentheses around that entire denominator. all right, so that you can punch it right into the calculator. Let me punch this guy in. So I get 34,650. Okay. Same thing here. If I'm talking about a permutation with repetition, you have 5 red, 3 blue, and 2 green beads to arrange on a keychain. Notice there's that word arrange. We're putting them in a specific order. How many different arrangements are possible? And again, it's repetition because if I switch 2 of the red beads, that doesn't change the result. I can't tell the difference between one red bead and another red bead. All right. So the idea here is basically I have, let's see, 10 things total. So it's a 10 factorial. But then there are 5 red beads, there are 3 blue beads, and there are 2 green beads. So I represent my repeated values, and now I simplify. The 10 factorial can reduce with the 5 to give me this. And then I have the 3 factorial, and then another 2 factorial. Oh, here's a 6, canceling with a 6, and maybe I could reduce the 2 with the 10 and get a 5. And now again, job for my calculator. And you don't have to reduce as much as I did. You could go right to plugging some of this into the calculator if you would like. So I get 2,520. Okay. Another great example, and maybe you like to do this, play with your food a little bit. You have 1 purple, 2 red, 3 yellow, and 4 orange Skittles. If you line them up before consumption, how many different arrangements can be made? And again, all yellow Skittles look pretty much identical, all right? Maybe one of them got like a chunk taken out of it or something, or the S is worn off, but let's assume that, those are pretty much identical. So when I look, what I have here is on, where was I here? Let's see, 10 total objects, so that's 10 Skittles. And now repeated values, I have 2 red, I have 3 yellow, and I have 4 orange. Notice I didn't include the purple because the purple's not repeated, I only have one of them. If I want to put a 1 factorial down there, it won't change anything. Now let me reduce it, let me simplify. So if I cancel with the 4 factorial, everything from 4 on down cancels. And then I'm going to continue to simplify. Here's a 6, can cancel with this 6. The 2, again, I'll cancel with the 10 to make a 5. And again, I just do that because it's a little less for me to plug into my calculator. So I get 12,600. Okay. Now let's talk about what happens when order doesn't matter. When order does not matter, we're going to use a combination. In other words, I reach in, this is that bag of marbles example. I want to know how many ways I could get one of each, a red and a blue. It doesn't matter if the red one comes out and then the blue, or the blue and then the red. All right, the result is the same. I have one of each of those colors. Okay, and notice it's the same as the permutation formula, except we have an extra r factorial in the denominator. So let me show you how this looks when we do it by hand. So let's see, that would be 7 factorial over 7 minus 2 factorial, 2 factorial. So I just add an extra factorial down there. So now I have 7 factorial over 5 factorial, 2 factorial. The 7 factorial and the 5 factorial reduce. Everything from 5 on down cancels out. But I still am left with the 2 factorial underneath here. And now I can finish simplifying this thing. That gives me a 21. All right. Again, once again, we can do this on our calculator. I've already got it pulled up on the Casio. If you're using a TI calculator, you navigate to the same place. So here, math over to probability, and then you'll use the NCR button. But of course, I did the silly thing and forgot to punch in the 7 first. So I'd have to do 7, then math over to probability, and then down to number 3 this time. And again, regardless of the type of calculator you're using, look for the probability menu. You'll type it in the same way. All right. Over here on my Casio, I punch in the 7, and then F3 for the combination button, and then the 2, enter 21. All right. If I want to do the next one, same kind of thing. I'm going to do it on the Casio just because it's already pulled up. But make sure you type in the 8, then find your combination button on your calculator, then the 5, then enter. That gives me a 56. Okay? And so here it is. Here's the idea. How many ways can a team of 5 be chosen from 11 athletes? And see, unlike when we're placing things and we're talking about first, second, and third place, that kind of stuff, this time we're just choosing a team, all right? And it doesn't matter if the team is chosen in a different order. If it's the same 5 people, it's still the same team. It's still the same result. So that's when order doesn't matter, okay? If changing the order changes the result. So here I do the combination. There are 11 athletes, and we're picking 5 of them. So it's 11, choose 5. And you'll notice that these numbers are quite a bit smaller. So again, type in the 11 first, then the combination, and then the 5. And notice that's a 462. That's quite a bit smaller than the types of results we were getting with the permutation. It's because it's basically taking out anytime we change the order, it's not counting that as a separate thing, okay? Whereas with permutation, when we change the order, it's counting those as separate results. All right, but now it's not. This one, a group of 7 campers are attacked by aliens. The aliens abduct 2 people and leave. How many ways can 2 campers be chosen? Again, it doesn't matter what order they're chosen in. What matters is which 2 campers are chosen. All right, and so if Jim and Bob are the 2 that get abducted, it doesn't matter if it's Jim then Bob or Bob then Jim. The result is the same. Jim and Bob are going to be gone for a while. Okay, so the combination of 7. And then it's choose 2, okay? And again, on the calculator, you punch in the 7, then the combination button, then the 2. You hit enter, and you get to 21. All right? This one, 5 cards are drawn from a standard deck of cards. How many hands can consist of 3 clubs and 2 diamonds? And see, the interesting thing here is I'm choosing from 2 distinct categories. I'm choosing from the clubs, and then I'm choosing from the diamonds. I have to do a permutation or combination for each of those. So let's decide, does order matter? Again, I'm trying to talk about the cards I have in my hand. Does it matter what order I receive those cards, or does it only matter which cards I have? And the answer is it only matters which cards I have. So order does not matter here. I can get the cards in any order. What matters is which cards I have. So what I have to do is I have to do a separate combination for the clubs. So I have to do the clubs. And then I also have to do the diamonds. And so for the clubs, if you don't know this, there are 13 clubs in the deck. And if you don't know this, there's 13 diamonds in the deck. So for the clubs, there are 13, and I want 3 of them. And then for the diamonds, there are 13, and I want 2 of them. Okay? And so I find these 2 combinations, so 13, choose 3. That's a 286. And then I also have to do the 13, choose 2, which gives me a 78. But now, what is this answer? Do I leave 2 separate answers? Well, here's the key. See what word I see here? The word and. All right? And you can think of this 2 different ways. You can think, well, an and is when I multiply probabilities. And it's the same thing here for the possibilities. Okay? So and means I multiply. You can also think of it as the fundamental counting principle. See, basically, there are 286 ways I can get the 3 clubs. There are 78 ways I can get the 2 diamonds. How many ways can I get those 2 events to happen together? I multiply. That's my fundamental counting principle. Okay? So the 286 times the 78. So to get all those things to happen together, it's 22,308 possibilities. Okay? So if order matters, we use a permutation. If there are values that are identical, it's a permutation with repetition. And if there are values, and if the order doesn't matter, then it's a combination. Okay?